Okay, yeah, thanks for joining the complex geometry informal seminar. So this is our third time to discuss. So far we had discussed just two objects. One was the we our like the current target is to study the so-called the four classical invariant metrics, including what was it? Kobayashi, Cartier-Dori, Bergman, and Kähler-Einstein metric. And indeed, it varies on our like the mathematical background and our expertise. And at least all those four invariant metrics are defined in terms of the complex structure. So complex geometry inevitably plays an important role. So we first look at the so-called the Calabi conjecture to study the complete Kähler-Einstein metric, but at the same time to understand the basic language in complex geometry. And in order to do it, so last time we talked about what's the definition of the complex structure and what's the definition of complex manifold and so on. And I thankfully received the request from Bharat last time that it's good to also look at the Chern connection in the seminar. I think this is also directly related to the like the Calabi's conjecture. So today, let me try to explain, but not in a way to just give everything very rigorous, but still I'd like to cover the actually some part of the rigorously so that you can check the details. So we have a now started the seminar, complex geometry, informal seminar. Three. So by the way, this is not indeed just a lecture. So this is for our conversation and discussion. So please feel free to interrupt if you have any like the comments or if you wanna share your own taste or appreciation. I really would, yeah, appreciate it. So let's just review what we discussed last time. So we start from basically just a smooth manifold, and we just have so-called complex structure. So the complex structure here just means that we just look at the just the definition last time. So let me just briefly just mention. So this is the endomorphism between the real tangent bundle to itself. So such that so J square is equal to negative identity, and this is we call the almost complex structure. So with the pair, so we should say almost complex manifold because we didn't guarantee this is complex structure yet. So that the way to think is we'd like to change the real manifold to the complex manifold, and we'd like to go from one to the other back and forth basically. So if we choose arbitrary point, so let me take P here. So we have a real like the tangent space that we know how to handle from Riemannian geometry, and we'd like to view this as a complex vector space. So the way to do algebraically is just to take the tensor by C, and what we consider is that we just split complexified tangent bundle into two pieces. One is so-called the 1, 0 part. The other is the 0, 1 part. We just split into those two pieces. So this was defined as a so-called C-span of the DDZI, and the other is the C-span of the DDZ I bar, so we have a linear isomorphism given by the complex conjugate from go one to the other. So now we can simply just take the projection. Basically, we just take the projection to the first part, but time to time we also can take the second like the projection to consider the anti-holomorphic part, depending on our like the context and the preference, so that we just will project down to here. So as a real vector spaces for each P, so it has the same finite dimension like that, so that we can just we already established the vector space isomorphism over here, but over C is completely different, and we want to preserve the so-called Lie bracket in order to consider the geometric structure over C. So the way to um, link from one to the other is that if we have a like the tangent vector or the local vector field, either written as ddxi or ddyi. So in this context, we just look at the just a basis over real. So we just map each as a so-called DDZI, and this guy will be mapped as a I times DDZI. So I just write just I in the manner that I use the index I in the different way. So those are as a complex vector space, DDZI and I times DDZI are no longer linearly independent. They are now linearly dependent because now we make the vector space over C. So in order to make this to be happen, then we should require that the dimension, real dimension, should be at least even dimension always. Otherwise, this J doesn't make sense. This is just the exercise in order to make J squared equals to negative identity. This M must be even dimension always. And therefore, we can just choose the local coordinates, say from x1 to xn and y1 to yn, basically, so that we were able to look at those like the local basis, but now we make it to be the linearly dependent. So real dimension 2n now becomes complex dimension n. So that should be clear by just this, that's the J. So at least now we have a linear isomorphism. So let me just mention it in a clear way. So we have a map from here to basically here for each P for sure. So this is a linear isomorphism. So the way to map is that if you have a general like the tangent vector x of p, so if you want to look at the local vector field, then you just need to eliminate this p and just look at the local neighborhood. So the way to change is we just have x minus imaginary number times jx. And then depending on the also the context, so I usually divide by just the two, just multiply by 1/2. But depending on the context, some of the like the paper also divide by square root 2 and so on. It's just about the scaling. So with that, this like the map, so we have this like the correspondence. So then now we change everything in the context of the so-called the holomorphic tangent bundle. So this is usually called by the holomorphic tangent bundle. So, but the rigorous definition is that we just collect all those like the V such that this J of V would be just nothing but this guy. So the imaginary number becomes the eigenvalue for this holomorphic tangent bundle so that we have a like the definition without using the local coordinate. And similarly for the anti-holomorphic tangent bundle, so this would be J of V equals negative imaginary number. So that because we have a linear endomorphism, so that we can just look at two eigenvalues and the corresponding eigen subspaces becomes just a definition, which does not require the local coordinate. So that we also require J to be complex structure at this point. This means, i.e., so if we have x and y from the holomorphic tangent bundle, then we want to guarantee that the Lie bracket should belongs to holomorphic tangent bundle as well. This is not guaranteed from the linear structure of the real tangent space in a sense that the Lie bracket structure is independent to the linear structure. So that even as a Riemannian manifold for the complex manifold M, so that if we just view that as a real manifold, no issue. But if you want to regard it as a realized as a complex manifold, then Lie bracket must be preserved. Otherwise, we cannot define the so-called the concept of the tensor, so that we cannot define the geometric objects. So tensor is required to define the geometric object as a tensor, so that it should not independent to the choices of the coordinate. And if you want to treat everything over C, then this condition is required, and this is the definition of the complex structure. And last time we just look at the characterization of the which almost complex structure becomes complex structure. But this you can simply take this as a definition. And we will all require this most of the time. But if some of you later study so-called the context of the symplectic geometry, then we usually do not require, in at least the theoretical level, the complex structure, but they usually look at the pseudo, like the holomorphic curves or the almost complex structure in general. But still, all their examples are still Kähler, and in my opinion. So 100%, even they always look at the Kähler, but they're like a or like the context, they look at just the almost complex structure. So that's what we last time discussed up to here. So any other questions or comments up to here? Okay, then let's just now move on to the Hermitian metric. So the Hermitian metric. So now we make everything over C. So let me say the pair Mg be a complex manifold. So now this is our starting point. So the Hermitian metric, so it also depends on the context, but when we talk about the Hermitian metric, so that this metric is equipped on the holomorphic tangent bundle. So not the real tangent bundle any longer. So this Hermitian condition just means that, so i.e., if you choose any sections, or you can simply just regard it as a like a vector field if you are familiar with that, like the terms. Then if you choose any UMV, then we require that UV in H should be the same as VU with the complex conjugate. This is a condition of the Hermitian metric. So still we'd like to do Riemannian geometry, so that we'd like to say there is a Riemannian metric as a real manifold associated with this H. This is what we'd like to claim. Then the way to do is, because this we realize is still the real Riemannian manifold. So that means that if you choose any vector fields, so we define Gxy. It's just nothing but we just plug in UMB that you can imagine what they should be, and just simply just take the real part. Here, as you can imagine, this U should come from the map we already defined, because we already have a one-to-one correspondence. So therefore, if we have the U and B and X and, or X and Y, then we can just take one to the other by using this relation, because this is our linear isomorphism. So same for this V. Yeah, hopefully this looks now clear. And now we are already recording a complex, we already have a complex structure, so that it should be fine. So this is a not difficult at all, but I should say exercise, because it could be helpful. Time to time, it could be confusing without doing this exercise, in a sense that time that we look at the real Riemannian metric, time that we look at the complex Hermitian metric, so that if you write this H Hermitian metric as so-called A plus IB as a Hermitian metric, then the corresponding Riemannian metric would be, now this is, you can just assume this is n by n for H, then G becomes 2n by 2n, because now we change the field, so that it becomes A, B minus B, A. This is just nothing but just using the definition. It's just a quite an actually trivial exercise, but very helpful in my opinion. So I will skip to check. Of course, I'm very happy to clarify if any of you try to do it and if you have any questions here. So now let's just look at the basic properties of this G. So for example, if we plug in same vector fields, X and X, then we know what we should require. So then according to the definition, then we are just plugging in these two. Then still this was the Hermitian metric. This is already positive, because we plug in the same vector fields, even though now we are working over C. And we still take the real, it doesn't matter because it was already positive here. But anyhow, this is positive because we require H was the Hermitian metric, the eigenvalues are already positive. And if you look at, for example, this guy, then we require this to be symmetric. Otherwise, it cannot be the Riemannian metric. Then this is defined as a H of these two. And take the rear. And now we have a properties of the Hermitian metric, so that we can change these two and take the complex conjugate, because it's a Hermitian metric. This is guaranteed. Then this condition is just the same as just nothing but GYX. So you can just easily just check. So, and moreover, so we talked about this last time. So if you plug in not X and Y, but if you plug in each for J, so last time we start from the Riemannian metric. So now let me start from here in the the backward procedure. Then according to the definition, this should be same as H of these two, and take the rear. we'll get that. And because we choose all sections or the vector fields from the holomorphic tangent bundle, then we know that they are just the same as just nothing but this guy. With the rear. And because when we take this out, this should be taken as a negative imaginary number multiplied by I, it becomes just a positive one. So that this will be same as a real of H of the without the imaginary numbers. So this would be the same as a G of XY. So this is the way that if you look at the just a consequence, if you require this for any x and y, g of xy equals g of jx with jy, then what we did last time is then we can complexify everything so that you can either start from the real manifold with the real Riemannian metric G requiring this condition, and I said this is a so-called Hermitian condition, then we can define corresponding H. And conversely, if you start from H, then by taking just a real part, then we have a Riemannian metric. But still, we should require for the Hermitian metric, these conditions. This must be equal to this guy. Then we can complexify, then you can start from the real manifold to get the complex manifold and back and forth. Is that okay with you? This is the necessary condition for the Riemannian metric. So the Kähler metric that we always consider is a special type of the Riemannian metric because Riemannian metric does not need to satisfy this in general. So now we have a definition. So last time we also defined.
Hello.
Yeah.
Yeah. So this condition says that the map J is something, somewhat orthogonality kind of thing, right?
Sorry, can you repeat again?
This map J, so it's behaving under G look like isometry, right? Isometry of
Yeah,
the
so
tangent
this
space, like kind
J
of.
behave as a G, so J is a so-called orthogonal transformation. So that intuitively speaking, we just rotate 90 degrees for each X and Y. Still, we should measure the same thing.
On the tangent space, yeah.
On the tangent space, right? On
Yes.
the real tangent space.
Yeah, yes. Thank you.
Yeah, this is sometimes very confusing when we proceed the real calculations. Sometimes we work over real and we sometimes work over C. So that can be distinguished in the easy way that if you use already ddzi and I times ddzi, then you already work over the holomorphic tangent bundle. But if you take these like the basis, ddxi and ddyi, then you actually take the real like the perspective. But it is confusing in a sense that for the real perspective, the metric you already choose should be the 2n by 2n matrix, whereas the complex case, you have just an n by n. So please don't get it confusing for.
Yeah.
Yeah, this is about in the real calculation. I kind of very confusing on this. Yeah.
Yeah. Thanks.
So, and I also want to make sure that even though this is very clear, but I just want to make sure that our definition that we made does not require the local coordinate. Holomorphic tangent bundle does not require the local coordinate, so it just has the description without the coordinate here. And same for the description of the Riemannian metric. So Riemannian metric. So because Riemannian metric for this definition, all we need is just this isomorphism. If you have this isomorphism, then we can just define just a real metric here. And still, we should get we should require that this J should be compatible with the complex structure. Without it, we cannot go from J to G to H and back and forth. That's not possible. So this condition is so that the key. I personally prefer to start from the real manifold because I prefer to look at just a real geometry. Then I can simply say so start from the Riemannian manifold basically Riemannian manifold so that there is already the Riemannian metric G. But all we need to say is that let's just require we have a complex structure compatible with the Riemannian metric. Then we can associate to the Hermitian metric H because this is equivalent information. But you can start from the complex manifold if you want, but I think you now understand what I'm talking about. So what we also discuss is we define so-called the fundamental form omega. This omega is defined as for each tangent, like each vector field, I'd like to say, so that you can also interpret this from the description. So all we do is because the starting point here is we start from the Hermitian metric. This is all we have. So from the Hermitian metric, what we do is we just plug in inside of HUMV. Now you know what UMV should be. This is much clear. But here is a very subtle point. So we should take the imaginary part, not the real part. Imaginary part. And in my convention, I should divide by -1/2. So this could be quite confusing for the complete beginner in a sense that, so it makes sense to take the real part to consider the real inner product, but complex geometry, we need to also look at the imaginary part somehow separately. And let me call this guy by the fundamental form because I didn't record this yet as a Kähler form yet. However, many papers call it either the Kähler form after requiring the necessary condition, and this is also called by the symplectic form. But if we call either these two, then we already have the necessary the requirement for that. But this omega, let me call it by the fundamental form for our class. But most of the time, we just look at the Kähler form. So here's the proposition that so we in fact regard omega of x and y as just nothing but g of jxy multiplied by -1/2. So let's first check this proposition and think about what this really means. So just a proof, it's just nothing but using this definition. So let's just start from the right-hand side. So g evaluated j, x, and y. If you have this guy, then we know how to handle this. Then we have a h and just map by using this R linear isomorphism and take the real part. This is what we know. So if we write this way, then we also know that, so now this J plays a role, J plays a role. So if without this J, then we know that it would be just the same, but because of this presence of this J, so this must be same as I times H of phi of X with phi of Y with the real part. Because J of X, X is the eigenvector with respect to the imaginary number I. Is that okay with you? So that's what we saw. So this is what we already know. So therefore, we can simply just take I so that we should get this guy. We should get this guy. And if you try to write it, and let me just write this by UMV, then if you write this H of UMV as a plus IB, and we multiply by the imaginary number, and take the real part, that should be the same as a negative imaginary number, imaginary part of the UMV. Because we multiply by I, so that it makes just a negative B, and we take the another negative sign so that it just becomes B. So they are the same. But what is this guy? This guy is just nothing but, if you look at this definition of the omega, so this is just nothing but omega of x and y multiplied by 2. Just definition. So and the proof is over. So now you can see the key, one of the two features from this proposition. Number one, so for this G, of course, this G matters as a Riemannian metric, but no complex structure inside. Whereas this omega, in order to define this omega, then, so if we define fundamental form in this way, then we already plug in complex structure inside because it must be equal logically speaking. So why do we care? So here's a remark. The reason is that we actually want to make everything, we want to make everything to be differential form. That's the key reason. So now if you look at, say, omega of y and x, just look at this. Now we have a proposition, so we can simply just use it. So this equals, sorry, I think I made a mistake. So it's just a positive 1/2, right? Yeah, just positive 1/2. So according to my professor, there's no sign. So also it depends, by the way, the convention that some of the reference use not jx with y, but x with jy. But I actually do not really care. So this is just about just a convention. So yeah, if I make the mistakes, so just in that case, let me know. So omega of y and x, then according to our proposition, this equals 1/2 of g of jy with x. We should get that. then what we know is that because this J is the orthonormal transformation with respect to this G, so that we can simply just act by J each time. This is guaranteed. Is that okay with you? Because we know that this G is compared with this J, then now we see we have a sign. Now we have a sign. Then we also know that because this G is symmetric, so that we can change the slot so that we will get negative 1/2 of G of Jx with Y. So once we get that, so that by applying the proposition again, this equals negative omega of x and y. So what happens? Now this behaves differently from the Riemannian metric. For the Riemannian metric, it must be symmetric. If we change the slot, it should be the same. Whereas now we change the slot, now it gives the negative sign. So we have a very fancy term to call this property. This is so-called the alternating two-form. So now this is handy in a way that now we can write down the fundamental form as a differential two form. This is a key. So that what we like to say is that so we actually have the following. So now let's just go back to our initial setting. So our initial setting was very simple. So we just require in our first two lines that we have a complex manifold M and G and the Hermitian metric, and we create the G and omega. So now let's just write down this H first. So this H is still Hermitian metric, so that this H should be written as so-called the two tensor, complexified two tensor. This is guaranteed. And we already said this H is a Hermitian metric, so that we should write in this way. So let's just write down in local coordinate, this H is written as this way, then this omega must be written. So the key is we actually keep this guy. Still, we keep this guy, and we change here to be wedge product. Wedge product, and here's the subtlety is we still need to multiply by the image number. Depending on the context, let me just divide by 2. So that this becomes so-called the real one-on form. One-on form means that so it has a one, this part, the other part is this one. So that's this one-on form. There's a special form, a special type of the differential two form. Not the DZI wedge DZJ, but for one type, there's no complex conjugate. The other, there's a complex conjugate. So we call it by the one-on form. So let's try to see why we put the image number. So indeed, if you take the complex conjugate, then it is clear that the first, like the coefficient becomes negative image number divided by 2 because we already have the image number, and we need to put this guy and dgi bar which dgj. So this is what we should get. So what we can now do is that now we can change these two with eliminating the complex conjugate, and we can also change these two with change the sign. So that the first part, we get ji bar, because this is a Hermitian metric, and the second part we should get dgj with dg this guy, and we need to just eliminate this sign. We get this. So this is omega. So this is now the real two, because it is invariant under taking the complex conjugate. So therefore, it should be the real. So now we have a definition that we already saw. So given complex manifold M, complex structure G, Hermitian metric H, we say M is scalar. M is scalar if the form we define, let me denote it by omega sub H. So this is induced from the Hermitian metric H, so that this is differential two form. So that it makes sense to take the further exterior derivative. This is identically 0. And also we last time discussed about the characterization of this guy by just showing you the references, but let me just also mention clearly so that those are all equivalent. So given a complex manifold, So we have M, we have J, we have H. So this algebraic condition of being so-called a symplectic condition for complex manifold, not the almost complex manifold, this is equivalent. First, if we take the covariant derivative on the complex structure, this is identically zero. These two are actually equivalent. And the way to check, I already mentioned how to check the reference to look at the detail. And this is actually really important condition I'd like to say. So when one learn Riemannian geometry, they first learn so-called the geodesic, and then geodesic is used so-called the exponential map, and the exponential map is defined the so-called the geodesic normal coordinate to kill the crystal symbol. However, Riemannian manifold exponential map is never holomorphic. It's not possible. Except just the plane, except the CN, that's not possible. So the third condition is that if for any point, they're so-called a holomorphic normal coordinate. So that crystal symbol is vanished at this point. So this is not coming from the exponential map. So i.e., this condition just means that if you plug in this point P, this behave indeed a Euclidean metric. And the crystal symbols are all vanished at this point so that we can do the geometrical analysis because of this condition. So if we remove this condition, it's still possible to carry out the necessary analysis, but it's just really annoying because we lose the holomorphic normal coordinate. And this condition is important for the potential theory because the potential should be written as so-called a subharmonic function, but let me do not mention as a subharmonic function, but just a smooth function for the beginners. So for this P, we have a neighborhood U of P. So we have a smooth function, but in fact, this is a Polar subharmonic function. F on U. So this is a local condition, by the way, such that the metric, Kähler metric, can be written as a complex Hessian for any ij. So then now we have a Kähler metric, and the reason that we need to make this setup is not only for introducing the complex geometry for the beginners. So the probably the most important, like the identity that we care, the following. So we have if we have a Kähler manifold, so now this is our real story about the Chern connection, given a Kähler manifold. So now let me simply just say M simply just a G. But already complex structure and H, all those are already omitted in this like context. And because we said our Kähler manifold is actually already Riemannian manifold, we already have a Leibniz connection, but we still need to talk about the Chern connection though. So this is important, like the detail that is not coming from Riemannian geometry. So Riemannian geometry, Lich curvature is so-called a symmetric two tensor, real two tensor. But in the Kähler world, this is no longer the case. This is in fact written as so-called a negative dd bar, partial dd bar, log of determinant of Gij bar. So still, this is a real one-on form. So here we use the description that the exterior derivative will be split as a d partial d plus partial d bar. So that we start from this function, and take one is with the complex conjugate and the other one without the complex conjugate. So this now becomes the real two form. And Lich curvature is now written as a differential two form. So that the metric that we care is differential two form. Lich curvature now becomes differential two form, so that now we can compare, not as a tensor, but as a differential two forms. Is that okay with you? And what we want to know is why this is the case. Of course, there is a way to go around to drive this relation. So the one of the standard way, if you look at the reference of the extremal metric, we can just use the Riemannian geometry. Then just write down the Lich curvature, then that gives the proof. But that's not what I'd like to do. What I want to do is let me introduce the Chern connection. And in the Chern connection, we have a basically line bundle, and the curvature form of the line bundle actually coincide with this expression. So, and this is very important in complex geometry because complex geometry not only care either the tangent bundle or the cotangent bundle, but it basically cares a so-called line bundle. So that we can look at the so-called cohomological description of the all quantities that complex geometry, several complex variable like community care. So this context is now different from the differential geometry, but it is the context of the algebraic geometry and also the symplectic geometry. So context is slightly different. So that in order to do it, I'd like to introduce the like curvature form of the line bundle. And in order to do it, I need to introduce a chunk connection. That's my context. So yeah, before I move on, yeah, this is sort of the review that we already saw. But yeah, please let me know if you have any questions up to here. All right, then let me now talk about the churn connection. So for the side remark, just side note, here is my knife, indeed knife. Um, I'd like to say example, not example for the churn connection, but it's about the CR geometry. It's about the CR geometry, and what I'd like to say is also sub-Riemannian structure. Yeah, so what's the point of learning either doing either several complex variable or complex geometry? It's all about solving Cauchy-Riemann equation. That's all. It's all about the Cauchy-Riemann equation. In order to solve it, then we need to require, if the function is written as a, say, u plus iv, then we require ux equals to, if I'm wrong, just let me know. I don't try to remember it. So uy equals to negative vx. This is a Cauchy-Riemann condition. And Cauchy-Riemann condition is also the equivalent condition of the almost complex structure and so on. So this condition is the pair. This is the condition of the pair. So if you take complex manifold as a two-dimensional ball, so this is a ball, C2, just satisfying Z1, Z1 bar plus Z2, Z2 bar is less than 1, then we know that we can equip with the Poincare metric that we first time we talk about. So if you just imagine the inside in the C2, inside here, we know that this is complete metric space. Even though we cannot see, we have a topological boundary. We actually should say ideal boundary because actually, technically speaking, we should not look at the boundary because this is complete metric space. With respect to the hyperbolic metric, and we know that this hyperbolic metric is either same as a Poincare or Carthy-Odori or Kobayashi, Bergman, Keller, Einstein, whatsoever, they are all the same in this context. But if you try to imagine, if you just look at the point near the just the boundary, so if you look at here, so what's the context? We already have the complex structure inside here. This J plays a role. But in order to make this to happen, this must be even dimension. Otherwise, it doesn't make sense. So that's why, because we already make it with the C2, this is R4. Whereas if you look at the topological boundary, this topological boundary should be homeomorphic to so-called S3. Or here, like the community, they usually call it by the SU2. Because as a manifold, they are diffeomorphic for sure. However, what is the context? We are not looking the interior here is a real Riemannian manifold. There is a context of looking at the complex structure. So the complex structure is already a smooth map in the level of the tangent bundle. So that we'd like to ask that if we can try to extend this complex structure up to the topological boundary. But this doesn't make sense. In order to define this complex structure, then we need to require the so-called even dimension already. It contradicts the fact that in order to consider the topological boundary in this way, then we should look at so-called real codimension 1. So it should be at least odd dimension. That's not possible to look at. So there's no way to extend the complex structure because of the dimension consideration. Then what's the way to do it? We should drop out the additional one more dimension on the boundary. so that we have a three real dimensional topological boundary, so that we are not able to extend the complex structure up to the homeomorphism or in the continuous way. That's not possible. So the way to do is we should extend this J to J to the topological boundary after the dropping out one of the additional dimension. This is we call the CR boundary. So view this as so-called the CR boundary. This condition just meaning that still we'd like to solve Cauchy-Riemann equation. After dropping out, additional one more dimension. Does this make sense to you? So that i.e. we view SU2 two perspective CR boundary that I need to explain what this mathematically really mean. So of complex two-dimensional hyperbolic space, and this actually just really means so-called the Hopf vibration. So now let me try to explain how to drop out one additional dimension naturally. So in the several complex variable, so there are also experts already here. So time to time, people look at the so-called the CR geometry. So there are few compared to the people working on several complex variable, but still there are the expert working on the so-called either the CR geometry or Sasakian geometry or sub-Riemannian geometry. And this is the one of the model space. So the way to think is the following. So the Hopf vibration, just a very naive introduction today. So you have so-called S3 sit inside of C2, sit inside C2. So all this like the pair satisfying this condition for sure. So what we do is we just act by the Lie group action by this S1. So the Lie group action is precisely defined as e to the IT with this guy is defined as just nothing but the complex multiplication in this way. Then what we can now see is that, so then it gives the quotient space by this action. Quotient space by this action. Then this is same as just a P1. So i.e., we have a map from S3 to P1 with fiber given by S1. So that this is the way to drop out the real one dimension in a natural way. Does that make sense to you? So in order to consider the complex structure in the level of the S3, then we need to know how to drop out the one direction. So otherwise, the structure from this J cannot be preserved nicely. So the way to do is we use this structure so that we have a fibration from S3 to P1. So in general, so if you want to look at the higher dimension, so we always start from the even dimensional sphere as a CR boundary of the complex hyperbolic space if you want, then this maps to where n-dimensional projective space. So by just looking the same consideration. So also we can map, we can also take the Lie group action by S1, then we can play the same game. Then now you can actually see why this is very important. So we have so-called the standard contact form. Standard contact form. So say this is, or let me just denote this by eta. So eta is written as a I over 2. Over 2 is not that important. Summation k equals to n zk dzk bar minus ck bar ddck. So this is differential one form. This is differential one form. Sorry, I think I am correct. Let me just, yeah, Yeah, I think I am correct. It's 2n plus 1 should be written as, sorry, it should be written as maybe 1 plus 2, n plus 1, n plus 1. So that for S3, there are two coordinates. Yeah, this is, I think, the correct expression. So then it's important exercise. Then we have this map. We have this map so that you can take exterior derivative. You can take the exterior derivative so that we create the differential two form. Then we can take the push forward so that it becomes differential two form on the codomain. This coincide we call the so-called the Fubini-Student metric as a Kähler metric, as a Kähler form. So first, this standard contact form recovers the Fubini-Student metric on CPN. That's one thing. And the geometry of this corner is coincide, I'd like to say. So this is as a manifold, as a smooth manifold, I'd like to say, as a smooth manifold. It's a bit like the over exaggerating though. So this is this guy. And the vertical part, so TRS1. So the always the vertical part we know how to drop out. So when we study the hyperbolic complex geometry, CR boundary plays an important role. And the CR boundary is actually coming from the structure of the Hopf vibration. So that's I just wanna mention. When you talk about the Chern connection, so that there's a behind connection so-called the Tanaka-Webster connection. So this is a connection defined on the Hopf vibration, on the CR boundary. This is very ugly if you look at it. But this is just coming from the context that still we'd like to solve the Cauchy-Riemann equation on the boundary. Then in order to do it, we need to drop out one dimension as we already saw. And that consideration is considered in the definition of the Tanaka-Webster connection. This is the canonical connection for the either the SU2 or the odd dimensional sphere or the Heisenberg group or the SL2R or the in the world of the so-called sub-Riemannian geometry, because we do not want to look at the full tangent bundle, but just a sub-bundle in that context. So, and this is called the standard connection of the CR geometry. But this seminar is basically for the complex geometry, not the CR geometry. But if any of you are interested in, I can better talk about. So it seems I might not have enough time today to talk about the Chern connection. So I need to just postpone for that next time. But let me just talk about some story that you might care. So let me just say what's next. Of course, I should introduce the Chern connection for sure. So here's what we do. What's next? So if you have a complex manifold, so it's about the classification of complex manifold via Calabi conjecture. Calabi conjecture is now we are talking about how to set up the basic language. So the way to think is the following. So we start from the complex matter. So I already omitted the complex structure, Hermitian metric, Kähler metric, that kind of other things I just omit. And let me call Mn. So this n is a complex n-dimensional now complex manifold already. Then what we can look at is we can look at this guy, holomorphic tangent bundle. Now we know what this is. So there's no issue here. So in the linear algebra level, so that we can also look at each dual space in each like the fiber-wise level. So this is so-called the holomorphic cotangent bundle. But this is not preferred notation from the people of algebraic geometry. Algebraic geometry people prefer to denote this by this way. This is the notation, but you can just interpret it back and forth. So now what we do is we want to take so-called the determinant bundle. Take determinant bundle. That means that we can take this guy wedge with n times. So if you take the n times wedge, this becomes real rank 1. So that this is usually denoted by k sub n. So this is usually called the canonical bundle. Canonical bundle. So it has a rank equals 1. This is a good exercise to really check. So local section of Km should look like with the local coordinate. Look like it's just nothing but dz1 wedge up to dzn. There's no complex conjugate here because we take the dual of the holomeric tangent bundle. So we just change this guy as just this one. Sorry. This one as just a dual. It's just a dual. So that we just take the n times wedge so that the local section only determines the function. Here's the function. So this function, because we don't require this to be holomorphic yet, so this local section, this f is just a smooth map yet. Just a local neighbor. So this is the form of the local section, so that we equip with, I'd like to say, the Hermitian metric H. So make sure that I am not saying this Hermitian metric is the Hermitian metric defined on the complex manifold. That's what I'm saying. What I'm saying is fiber wisely for this canonical bundle because it's a complex dimension one. Complex dimension one. I equip the metric over there, not on the in the level of the holomorphic tangent bundle. So please do not get confused about that. So we will do is we just change this context slightly. So we put G here. We already have a Hermitian, I can say either Hermitian metric or whatsoever, but now you understand the context. So this G is a Riemannian metric or the Hermitian metric whatsoever. Right? So this metric is the following. This metric is written as 1 over determinant of G. I need to explain why. This is the Hermitian metric. So this seems non-trivial that I should explain, and this is related to the context of the Chern connection. Then what we will get is the following. So we will get, I'd like to just say just one word today. So its curvature form is just nothing but I dd bar log of h, which equals negative I dd bar log of g. And if you look at this remark, this becomes the Lich curvature that I need to clarify each of them. So the classification of complex manifold has 3 big classes. Number 1, Fano. Number 2, Calabi-Yau. Number 3, general type. Of course, it does not mean that, in fact, there are the extras. It does not mean that 3 classes cover everything, but still, these are very big classes. So that this is the case if each of G, so let me just now require, this is compact Kähler. So if this is positive for some G, for some, let me say, Kähler metric G, in such a case, we call it by the Fano. the example, CPN. That's the example. And Calabi-Yau, if reach of G is 0 everywhere. So examples, elliptic curves, K-series surfaces, and hyperkähler. All of them are highly important in many, many different like the areas. General type, if reach of G is negative. So the example, for sure, complex hyperbolic space. Complex hyperbolic space. And then the Yau's like the contribution is solve these two by using the Calabi-Yau's conjecture. So Calabi-Yau's conjecture covered these two classes. These two classes, they are completely solved by just using the Yau's original like approach. Final case, not solvable in general. Because there is a algebraic geometric like the obstructions that there is the class that one cannot really solve to determine this like the final metric, and there's a big story around. And in order to consider it, then we just look at this guy, and this context is coming from the Chern connection, and the invariant metric business are related to the general type basically. So the contexts are slightly different depending on the sign of the curvature, sign of the, I should say, Leach curvature, and the Holorn sectional curvature also plays an important role. So and in order to do it, we first try to understand what is the Calabi conjecture first, and then look at each like the classes and so on, depending on our like interest to look at. So yeah, so I think today I just need to stop here because of the time. But if you have any like the questions, and I'm very sorry for the very like the rough like the sketching the just a story that I have in my mind, and yeah, I know it's very like the crush like the introduction, but still could be I don't know, not useful. In that case, you can just ignore. So yeah, let me know if you have any questions or comments up to here. And next time, let me talk about the Chern connection. Sorry for that. Yeah, if not, let me then stop to record.